Kia ora team. I feel as I'm live now, and because of that, let's begin. So just comment in the chat just to let me know that you are here and you can hear me and the volume level is okay. So in this live stream, I want to cover first principles because that's the wrong color. First principles is the foundation of how differentiation works. Okay? The first principles of differentiation. Actually, there's first principles of a whole bunch of other types of mathematics, and first principles of differentiation is what we're going to look at, but we'll just call it first principles from now on. Okay, thank you, Harry, Max, and Kate. This is awesome. So, first principles is how do we get to differentiation? How do we get to what we learnt in level 2? And I don't want to start with what we learnt in level 2, but I'd rather start with the idea of why we do differentiation. And more basically, differentiation is the study of change. And so, hi Jackson and Oliver, because of study of change, okay, the word study looks really, really badly written, so I'm going to write that again. Because change is so important to us, we're going to look at all instances we've looked at change. And so change for us, well, I'm sorry guys, my pen's like skipping a few steps. Change for us has been in rates, slope used to describe change. How fast does something change? How quickly does something change? How steep is a curve? So that's where I want to look at. So I'm going to draw a rough sketch of a graph. Okay. Here's a line. I'm going to ignore this bottom part, okay, because that was mildly traumatic. So I'm going to call this equation, and just humor me here, I'm going to use functional notation. I'm going to call this f of x equals, suppose this is 2x plus 3. Okay, I know the gradient doesn't look like 2, but I don't have a scale, so don't worry. Okay, so suppose that's the equation. Now, if I had 1, 2, 3, 4, what would you say the change, the vertical change between this one and this one is? Between x equals 1 and x equals 2. Oh, hey, Caitlin, how are you? What is the vertical change? And then tell me, how would you find the gradient? So, what I could do is I could plug in x equals 1. And so I could find what f of 1 is. What's f of 1? That's 5. I can find out what, sorry about that, find out what f of 2 is. And what's f of 2? 7. Right, but I'm just going to write it as f of 1 and f of 2 for now. Right, and so then what I can work out is, well, the I'm going to use a different color for gradient. All right. The gradient is equal to the rise over the run, or the change in x over the change in y. Some of you have noticed this as delta x. Oh, sorry, change in y over change in x. Sorry guys, it's Monday. It's not Monday because it's Wednesday, but we're going to call it Monday, okay, team? So change in y over change in x, right? And change, that's the same letter as the capital letter delta. That's the same as the one we used in discriminants last year. So I want to maybe recall you to this notion where we used m for gradient and we had change in y. We had y2 minus y1 over x2 minus x1. And that's how we've always done gradients, right? Change in y over the change in x. So in this example, I have my gradient is equal to change in y is equal to, what was it, 7 minus 5 over 2 minus 1, and that's 2 over 1, so my gradient is 2. Pretty easy, right? And in fact, some of you might be pointing out to me, Mr. Dharma, you could have just looked at the front number. And yes, that's true. But for the purposes of what I'm trying to get at is how gradients relate to this equation. So I'm going to ask, let's write it in a more general case. We're going to write the gradient equals y2 minus y1 over x2 minus x1. Can I just reframe this a little bit? Can I reframe this and erase some of these labels? And pick some different points and see what happens. So what if I just had some generic points instead of these very specific ones? Okay. Suppose I had f of x, and we'll call this point x. And then let's call this point let's add a bit of a distance. Let's add h. So what's this point here? This point is x plus h, isn't it? And so then, in turn, what is the value here? If this is f of x, what is this one here? Sound off in the comments. So I'm hoping some of you said this is f of x plus h, because it's just the function's value at x plus h, right? And so if I wanted to find the gradient between these two, I could use y2, which is f of x plus h, thank you, Eddie, minus f of x, so that's the change in y, so that's this part here, over x plus h minus x. Can we simplify the bottom for a little bit? do you notice that the distance between the bottom is just h? So I've got f of x plus h minus f of x all over h. And this, thank you, Jackson. Yes, that's where the h comes from. It's just a distance. It's a small distance. And so this is the gradient operator. You know, this is how we've understood gradient. The change in x, the change in y over the change in x. And I'm going to just offer a little bit of insight. Over here, we had capital delta, change in y over change in x, right? I'm going to then say that notation-wise, if this is a change, how can we indicate a little change? Well, if this is capital delta, d, then this is little d, little change over little change. So that's why we've got dy over dx in the same kind of way. Change in y over change in x over a small distance. And so this is an idea of gradient. And you can always get the gradient using this kind of idea, getting the difference between these 2 points over that horizontal distance. And that works well for straight lines. That works really well for straight lines. But for curves, it doesn't work so well. Because if these points are too far away, well, let's have a look. Let me draw a graph for you. Okay. Oh, okay. I know it's pretty trash. I'm sorry, guys. Okay, but let's go from here. Let's pick 2 points. Let's pick this point here and this point here, right? Fortunately, it kind of looks straight. But if I were to draw a straight line between them to approximate the gradient, what would happen is, if I had this straight line here, if I were to try to approximate the gradient at this point here, which I will do in green, that the slope of that green line and the slope of the blue line are quite different, right? And as I move this point closer, my gradient becomes closer and closer to the gradient at the point. But remember, we want to know what gradients at points are. We don't want to know what a gradient between 2 points is, because that doesn't make sense. That's not very exciting. And that's sort of what we're looking at in differentiation. So what I'm going to do is I'm going to cut to a Desmos graph of exactly the same thing, and I'm going to show you what happens when that distance between those 2 points gets smaller. Okay, so let's try that out. So I'm trusting that now you can probably see a Desmos screen. And I hope you can see it clearly. I'm just going to hit projector mode so that you can see it a little bit more clearly. Can you just sound off in the comments, say if you don't want projector mode, because I can do that too. This is in projector mode now. Now I have this black line, which is the parabola I drew, this purple line, which was the blue line I drew, and look at how, if the green line's the gradient at this point, the slope of that point, look how far the purple line is to the green line. And watch what happens when I move this blue point closer and closer. What's happening to the gradient? What's happening to the purple line and the green line? If the green line is the gradient at the red point, if I move this blue point closer and closer to the red point, the green line and the purple line are becoming the same. So I'm getting a good approximation for the gradient at that point, the slope at that point that is tangential to that red dot. But what happens when I make the blue dot at the same spot as the red dot? Let's see, I'll drop this here and see what happens. It's very close. But if I drop it exactly there, the distance between them is nothing, and the purple line disappears. That is because, how do you find the distance between 2 points? Getting closer and closer together. Oh, nothing's moving, sir. Oh, crumbs. Yo, that's some tragedy right there. That's really sad. I'm so sorry. So I've been moving around things on my computer all the live long day, and nothing's been happening for you guys. I may as well just draw it for you then. Sorry. Thanks for pointing that out. I may have had yeah, soz. So I'm going to try and draw this picture bigger. I don't know why that wouldn't have worked for you. Okay, let's just look at this part of the parabola. We'll call this red dot, and we'll call this blue dot. Okay. As the position of that blue dot, and let me just find a tangent of this red dot. Okay. Guys, I'm sincerely sorry. I thought you could see what I could see. Can you see this? Yeah. I'll make a little video. This is a little video, but I don't know. I'll figure it out. Okay, so the green line is the gradient I want. But between the red point and the blue point, if I drew a straight line, let's use a purple pen. You can see the green line and the purple line are not the same. Okay, but if I move this blue dot closer, the line between the red line and the blue line is closer to the green line. And that's kind of exciting, because look at this new line. And so let me just write up what I'm saying. I'm saying that the gradient equals and what I want to do is I want to make that distance, that horizontal distance between the red dot and the blue dot smaller and smaller. Okay, thanks. You can see the whiteboard stuff. I don't know why you can't see the Desmos stuff. That's really annoying. That's really good information though, because I was going to do Desmos stuff with my year 12s next week. So I want to make that smaller. So in essence, to find the gradient, to find the derivative or the gradient function, I would like the distance, the change in y, over the change in x, but I'd like to do it such that this h gets smaller, and we know some notation for that. We would like the limit as h gets closer and closer to 0. What happens when h is 0? You can't, because what we're saying is the blue dot and the red dot are the same, and that's not okay. And so we're looking at the limit as h tends to 0, and seeing how the equation goes down, and seeing how close to the gradient function we can get. Okay, you're like, Mr. Dharma, that's still a little confusing. Okay, let's use an example. Okay, an example that you might remember from last year. F of x is equal to x squared. I think last year you learnt that f dash or y dash or dy by dx is equal to, you multiply by the power and you take one off. So it's just 2x. And that seemed like a very mysterious thing. Yes or no? It was a kind of a weird idea and you didn't really know why it worked. Now let's try it with first principles. With first principles. Okay, so have a look. I'm saying that f dash of x is equal to the limit as h tends to 0 of f of x plus h minus f of x all over h. Because that's the gradient function, and we're just going to see the gradient function as that distance gets closer and closer to 0. And remember, I can't just plug in h equals 0 because it doesn't work. Because when h equals 0, it's 0 minus 0. 0 minus 0 is 0, and 0 divided by 0, it does bad things. So we don't want that, right? So let's plug in these things. So if f of x is equal to x squared, what's f of x plus h? I'm really upset that that thing didn't move. Like, I made a really cool graphic for you and all. But did it move? How dare it? Maybe I've got to make it more of a dynamic web page kind of situation. So I'll try to do that next time, okay? Thanks, team. Has anyone got an idea as to what f of x plus h is going to be? So, that was a phone call. I'm sorry. So, here goes. So, f of x plus h is going to be x plus h all squared. Because all I'm doing is substituting x plus h in place of x. Right? And, yeah. And Eddie, thank you for expanding that. Yeah, awesome. So, let's try it. So, we'll write f dash of x equals limit as h tends to 0 of f of x plus h. I'm going to rewrite that. F of x plus h is x plus h all squared minus x squared, because that's f of x, all over h. Now, can I plug in h equals 0? No. But I'm going to do what Eddie's done, and I'm going to expand. So this becomes x squared plus 2xh plus h squared minus x squared all over h. And that's how you expand the front part. And notice this and this cancel. And so now I have limit as h tends to 0 of 2xh plus h squared over h. Even now, if I plug in h equals 0, bad things happen. Because h equals 0 will still divide by 0. So we don't want to divide by 0. And if there isn't a divide by 0, we can plug in h equals 0. So what I'm going to do is I'm going to factorize the top. Factor an h out. So I've got 2x plus h. Okay, and that's really cool. And what I'm going to do is I'm going to write that as h over h times 2x plus h. And this h over h is not 0 yet. So since it's not 0 and it's only approaching 0, they're the same, I can cancel. And so now I'm left with limit as h tends to 0 of 2x plus h. What happens when h is 0 in this equation? Does anything bad happen? No. If h is 0, nothing bad happens. So, well, I substitute substitute h equals 0 into this. I don't need to write the limit statement anymore because nothing bad happens when h equals 0. And I get 2x. Hey, that's exactly what I expected to happen all the way up here. But it took a long time. And you're like, Mr. Dharma, this seems like an outrageous waste of time. Why would you ever go around this long-winded way of differentiating something? And I'm saying, no, you don't have to do this. You don't always need to do this. But this is where it came from. That's not how you spell from, Mr. Dharma. Okay, so I want to pause there because this is how differentiation started, and this is how polynomial differentiation started. And so if you do first principles, you can do first principles for everything, and it will give you the right answer. Okay, but this is like taking Thor's Mjolnir, like hammer, to put a thumbtack in a wall. You don't want to use first principles for every differentiation, but you can use this first principles differentiation to derive, and that's how they have derived it. How you derive every differentiation rule. But over the course of tomorrow and early next week, I am going to cover basic differentiation rules, and then differentiation rules for basic products, basic quotients, and basic functions. And I'm not going to go through and do first principles for them. I could, and that's how we could prove all of them, but I'm going to give you some facts. And after I give you the facts, you're going to go practice. Do I want you to do some first principles? Yes, I think it's beneficial for us to do some practice of differentiating using first principles. But what I want you to know is differentiation is simply finding a gradient. And now this is a gradient function, meaning for every value of x in your original function, f of x, for every value of x in your original function, f dash of x will give you the gradient at that point. And whatever your function looks like, I will tell you the gradient there, I'll tell you the gradient there, I'll tell you the gradient there, I'll tell you the gradient there, if it's differentiable. If it's not differentiable, remember, if it's got awkward peaks, if it's got breaks, these points are not differentiable. But if it is differentiable, first principles is how we differentiated, how they came up with the rules, but I'm about to throw a whole bunch at you in the next few days, and those are the ones we're going to start using. But this is how it comes. So what I'm going to do is I don't have any more to cover today. So I'm going to put up 3 questions. Okay? Let's have a go. By first principles, show the following. Okay, question. If f of x equals, should be in black, I don't know why it's in red. If f of x is equal to x plus 7, 2x plus 7, show f dash of x is equal to 2. Okay. Question 2. If f of x is equal to x cubed, show if dash of x is equal to x cubed, 3x cubed, 3x squared. Okay, Harry, I'm going to leave these two questions up. I'm going to put one more up and then I'll answer Harry's question. The last one, if of x equals x plus 1 squared, show if dash of x equals, I'm going to just write it underneath, guys. If dash of x equals 2x plus 2. Okay, give that a go. Harry, okay, so everyone try these, and Harry, I'll answer your question. Could there be any proof questions where we'd have to use this in the exam, that is? I'm not going to say no, but there haven't been in the last few years, right? But understanding first principles has been pretty important. Understanding limits. So you might not need to do first principles differentiation, but it might pay to know how to use limits and how to simplify using a limits equation. And essentially, first principles is a special kind of limits equation. But I wouldn't throw this away and not do it, because I think this is a fundamental part of calculus. If you want to say you know how to do calculus, you need to understand how first principles works. No, you don't have to always do it, because it gets real messy really quickly, as you will see when you get to question 3, or even when you get to question 2. I think question 2 will be interesting enough for you. But it's good to practice, okay? And that's why I've only suggested that you do almost one or maybe 2 questions of this as revision now. When we get back to school, we'll probably look at doing more practice of this. We'll probably do a lot more interesting practice and exam style questions in term 3 when we're doing study. Okay. So I'm going to leave those for you to do for a little bit. But in the meanwhile, just quickly outline how important it is for you to stay on task and stay on track with differentiation. We are going to learn new content every day for the next 3 weeks. Differentiation is a very content-heavy subject, but everything we learn builds on what we've learned before. So I wouldn't skip a lesson, because it's probably going to get a bit tedious. But I feel as though we've got a good amount of time, so let's make sure that we stay on track and make sure we ask questions when we need to, because that's really important. Your teachers are here to help, so let's do that. Okay, so what I'm going to do is I'm going to do question 1, and I'm going to leave question 2 and 3 as exercises for the reader, or I might speed through them and then you can slow this video down and watch. Okay, question 1. If dash of x is equal to limit h tends to 2x plus 7. Make sure you use your brackets. I think people mess up without brackets. Okay, and then all I'm going to do, this is going to be quite nice. I'm going to go h tends to 0, and I'm going to expand the numerator. Right, so that's 2x plus 2h plus 7 minus 2x minus 7. And watch this. That and that cancel. That and that cancel. Oh, sorry, this is all over, by the way. And so now all I've got left can cancel. And so I've now got limit h tends to 0 of 2. There's no h's in sight, so I can just write 2. Boom, done. And let's put a bit of box here, because that's cool. That's question 1. Ask questions if you can. Question 2 is a little bit freakier, so I'm just going to write it out a bit slower. F of x plus h is going to be x plus h all cubed, and I'm just going to expand that to save me some time. X cubed plus 3x squared h plus 3x h squared plus h cubed. Why I write it like this, I feel as though there's some cool stuff that I'm about to do. So I know how to expand that, and so let's go up and write up what's going on. F dash of x is equal to limit as h tends to 0 of, I'm going to skip this part, I'm just going to write the expanded form, x squared plus 3x squared h plus 3x h cubed minus x squared, because it's f of x. Right? Remember this part here, ooh, that's a bit dodgy. This part here is f of x plus h, and this part here is f of x. Okay? And then what I want you to do is notice that this part here and this part here cancels, and so you've got limit as h tends to 0 of 3x squared plus, no, not 3x squared, 3x squared h plus 3x, oh, 3xh plus h cubed all over h. And if you notice, I can factorize h out. So I've got 3x squared plus 3x h plus h squared all over h. And fortunately for me, limit as h tends to 0, h over h, that cancels. And then I've got this thing left over. And so, finally, because I don't have any issues with h being on the denominator anymore, and I've just got to substitute it into this thing here, this is okay to be 0, this is okay to be 0, and so all I'm left with is limit, oh, no limit, I don't need to write the limit anymore, just 3x squared, which is exactly what I wanted. Okay, you can pause that later on and, see how that unpacks. I think maybe if there are no questions, I will just do the last one as well. Okay, but if you have any queries, please ask your teachers or ask me in the comments. All right. I'll give you a minute to catch that up. I'm still gutted about Desmos, so I'll figure that one out, okay, guys? So this last one, all right, f of x plus h is going to be x plus h plus 1 squared, and if you do a bit of expanding carefully, you will get x squared plus xh plus x plus xh plus h squared plus h plus x plus h plus 1. If you're not sure how this one works, use a grid and you'll be able to expand it. But if you simplify it, the x squared plus 1, 2 xh plus x plus 2x plus, so let me just go, x squared 2xh plus 2x plus 2h plus h squared plus 1. Okay, that's all of what that is. That's a bit crazy. Okay, but I think it's pretty useful. All right, and then let's also just unpack what this expands to, f of x. F of x expands to 2x squared plus 2 x squared plus 2x plus 1. Okay, so let's put all of that onto our fraction. X squared plus 2xh, 2x plus 2h plus h squared plus 1, 2 minus x squared plus 2x plus 1, all over h. What have I forgotten? I've forgotten to put the limit at the front, and this is not okay. So make sure you always write limit at the front when you're doing this kind of thing. Okay, then I'm just going to expand x squared plus 2xh plus 2x plus 2h plus h squared plus 1, x squared minus 2x minus 1, all over h. And let's try cancel. Cancel that and cancel that. Cancel that and cancel that. Cancel that and cancel that. What am I left with? Limit 2x h plus 2h plus h squared. Surprisingly, a whole bunch of that just went. Fortunately, I can factorize. And they go. And once they go, you're comfortable, just plug in. And so I get limit as h tends to 0 of 2x plus 2 plus h. And that can go to 0. So, I don't know why that didn't change. So, this whole thing is equal to 2x plus 2, which is exactly what I wanted. And that was also meant to change to black. Sorry, team. Cool. So, I'm going to leave that there. I want you to practice this up. There's not many. There's only like 4 questions in the book. You can find a whole bunch more of this online, maybe on Education Perfect. Ask your teachers. But this is how first principles work. And to reaffirm what Harry was saying, don't overdo this. You don't need to be proficiently outstanding at this, but you need to understand how this kind of thing works so that when all the other stuff happens, you'll be a little bit more confident and comfortable that differentiation, the way we do it, is a better way than trying to do things by first principles. And I can promise you, try to differentiate sine of x with first principles, and you'll have to start using trig identities, and I think that's really cool. Actually, bonus points if you can differentiate sine of x using first principles. Okay? Differentiate sine of x using first principles. And I will, when we get back to school, give you a chocolate fish. All right? I will talk to you later. Thank you, team. If there's no questions, I'm going to end the stream. Oh, thank you, team. I'll end the stream. What about that? I am a lyrical genius. Okay, thanks, team. I'll wait for questions. All right. I don't think any questions are happening, but if you ask questions, I will answer them in the comments. Thanks, team. See you later, guys. Be good.